Hi everybody. Today we'll introduce you to our project named TerraSense. Because we recognized the challenge of the conventional terrarium monitoring, we decided to develop an innovative solution. And our vision was to create an IoT system that would make terrarium management much easier. We had an 11 people group split into three smaller groups. The first team focused on the cloud infrastructure and they took care of storing and managing the sensor data received from the IoT team. The second team was in charge of the front-end development. They used React to create a visually appealing and intuitive interface. Also, this interface allows users to visualize real-time sensor data and customize terrarium settings. The third team worked on the IoT aspect of TerraSense. We developed an embedded software application based on free RTOS, ensuring efficient utilization of resources and reliable communication. Also, through the implementation of LoRaWAN, our IoT devices established a long-range and secure connection with the cloud, enabling real-time data transmission and remote control. Here you can see the UI of our system, but my colleagues will present all the in-depth aspects of the project.
During this project, Agile was utilized as a development concept. It is a powerful methodology that allows us to deliver high-quality software while adapting to changing requirements and maximizing the product's value. It puts emphasis on collaboration, flexibility, and iterative development and enables the team to respond to feedback quickly and make timely adjustments to deliver a product that meets the needs. At its core, it puts value in individuals and interactions, work in software, customer collaboration, and responding to change over rigid processes and extensive documentation. The benefits of agile development are numerous. It allows us to deliver value faster, promotes teamwork and self-organization, and enables us to adapt to market changes effectively. As an agile framework, we have used Scrum, which is a lightweight framework that enables teams to deliver incremental value in short iterations called sprints. Let's dive deeper into how it works. Scrum defines three key roles. The product owner represents the stakeholders and ensures the team builds the right product. Scrum Master serves as a facilitator, supporting the team and ensuring adherence to Scrum principles. The development team, which is cross-functional, self-organizing, and accountable, does the actual work. In our case, both product owner and Scrum Master were fully fledged developers in this team. Scrum begins with sprint planning, where the team selects items from the product backlog to work on during the sprint. These items are broken down into actionable tasks. Once the sprint starts, the development team collaborates daily during the daily scrum, a short stand-up meeting. They discuss progress, challenges, and plans for the day. Transparency and communication are the key. These meetings were held individually by every team. At the end of the sprint, we conducted a sprint review where the teams presented the work completed, gathering feedback from the other teams and adapting future plans accordingly. Along with the review, there goes a sprint retrospective as well, which was meant to point out faults in the process and create a better environment for the oncoming sprints. We have decided to work with only 3-day sprints. Because of this, the amount of work we were able to do wasn't as significant compared to normal sprints, but it pushed forward the adaptability and flexibility.
This is the presentation of the front-end team, and we will start by listing the requirements we had to meet. The application must be developed using React. The application must be hosted and accessible online. The application must retrieve, parse, and display relevant sensor data. The application must include options for visualizing the sensor data history. The application must have a responsive user interface, and all customer-related features of the system must be managed through the application. We will start by discussing a bit about the design we chose for this project. We used Figma tool to design the initial concept. That is a very useful tool for conceptualizing components, color schemes, sizes, shapes, fonts, and so on. So we will jump straight to Figma. Unfortunately, there are features that didn't end up in the final product, since the initial concept was wrapped around the project description we had to do. So these are the feeding schedule and the list of the animals within the terrarium, and I will not stop on them. But I will tell you about the features like showcasing the ranges of sensors, showcasing the last entries of the sensors, and also showcasing the history data of the sensors in the form of graphs. Each of these is interactable or responsive, therefore the temperature ranges can be easily edited through the pop-up that would show when you click on edit parameters. The displays are also responsive and they will showcase the last entries there are, and the historical graphs are also responsive, since when the value goes beyond either of the limits, it would trigger alerts that would let the user know about the situation in a terrarium. Um, I would also stop a bit on the navigation bar that also holds useful information about the user and the list of terrariums a user has registered. Uh, Also, both of these can be editable, therefore you can see that the user can edit their credentials, and he or she can add the terrarium through this pop-up above. There are also other pages that I will not stop on very long. The login page and the welcoming page in case the user didn't register any terrariums yet. Going on with our presentation, we will talk about technologies. The front-end team decided to use the most popular languages for any web application development. That is the HTML markup language, the CSS designing language, and the JavaScript as the main programming language. Besides this, we also used some other tools like Node.js that helped us with setting up the development environment, and React.js. Besides this, it's Axios that would have helped us establish connection with cloud in order to send and retrieve data through REST API requests, but I will talk about this a bit later. And we also used Chart.js and React Bootstrap as libraries from which we imported different components to make life easier. For the mock data we used later on in the project, we used the Macaru tool that is a very useful tool to create random mock data in a very big amounts. For the project deployment, we used Netlify, and I will show you how it works a bit later. Going back to the presentation, and going straight to DevOps. I will not talk very much about it because mostly DevOps helped in this development process with Git and GitHub, since it provided a very useful way of being able to version control the system. But for now, we'll talk about testing. We used the Jest testing library as our main development environment. We used Visual Studio Code and, as I mentioned before, React and JS, and we decided not to use containers since the front-end team found it irrelevant to the development process. As for GitHub, we established a Git workflow and some rules for Git that I will not go through because we all discussed about it during the tuition period. I would rather go straight to the app. So, as I mentioned before, unfortunately, we weren't able to establish connection to the cloud because of API and course issues that I will show you in a second. So here we go to the login page where a user can easily log in. But as you can see, there is an error message for now, as well as in the registration. I will show you why it happens. Basically, again, we had issues with course. Basically, we weren't allowed to access the API requests because of course issues that I will not go through because it is not front-end related, but because of this we have the incommodity to not be able to navigate through pages right now through just buttons, and we will have to use the link above. So I will just show you the quick showcase of this main page we have. As you can see, everything has a pop-up. Unfortunately, they are not usable, but they are there. What is actually working are the temperature, are the ranges, the displays, and the graphs that will showcase the data when I will input it manually in our JSON files in a second. So first of all, let me show you that we also have filters that would showcase the data in real time. That would be the last 10 entries. Daily, that would be the last 24 entries, and weekly, that would be the last 168 entries. This filter works for all the graphs. So, going to showcasing the change of displays, I will just access the code for this. As you can see, we have a grave data JSON file with mock data. Let's say I just add another entry and edit the values a bit. So let's go for temperature. Let's go beyond the minimal limit. That would be, let's say, 16. For CO2 also, let's go beyond the minimum limit. That would be, let's say, 225. And when I save, as you can see, we receive alerts that message us the problems within the terrarium. Also, let me show you the change of ranges. So as you can see here, we have the ranges for temperature. I will just change them, let's say, from 18 to 20 and from 20 weight to 36. And when we save it, as you can see, it also changed. It went beyond the graph. Sorry for that. I have no idea why that happened. But it still changes. It dynamically changes within the graphs and the display ranges. And for deployment, we just go here.
Technology stack. For the technology stack, I will tell you more about technologies from the cloud side. Spring Boot. The project utilized the Spring Boot framework for developing the backend server. Spring Boot simplified the development process by providing auto configuration and opinionated defaults, reducing the need for manual configuration. It also facilitated fast application development with its built-in features such as dependency injection and easy integration with various libraries and frameworks. Docker. Docker allowed the team to package the Spring Boot backend server into self-contained units called containers. Docker provided isolated and reproducible environments for developers, ensuring consistent behavior across different setups. Docker containers facilitated seamless deployment by encapsulating the application and its dependencies, eliminating configuration issues. In this project, it was decided to use a relational database PostgreSQL in particular. PostgreSQL provides extensive documentation and constant updates on its functionality, security, and other features. Google App Engine was chosen as the deployment platform for hosting the Spring Boot backend server. It provides a serverless architecture, eliminating the need to manage infrastructure and allowing the team to focus on application development.
For middleware on our project, we used REST API, which connects a front end to the back end, and we used WebSockets to create a connection between IoT and backend. And now I'll talk a little bit about WebSockets. Real-time bidirectional communication is made possible through WebSockets, which offer a full duplex channel between a client and a server over a single TCP connection. WebSockets allow the server to start communication and send data to the client without the client expressly asking it, in contrast to conventional HTTP requests. Because WebSockets are ideal for applications that need real-time updates, we chose them. Because they do not require additional headers to be sent with each message after the initial connection has been made, WebSockets have less overhead than conventional HTTP queries. WebSockets allow for simultaneous message exchange between the client and the server, enabling interactive and responsive communication between the two parties. Secondly, I'll talk about REST. Due to its many benefits, we chose to use REST API for the connection between the front end and back end. As a stateless API, REST does not keep any client-specific information on the server. For action on resources, REST employs the standardized HTTP GET, POST, PUT, and DELETE methods. This gives client a dependable and understandable user interface. Communication between backend and front end is ensured thanks to the REST API, which is perfectly suited for web development.
For our GitHub workflow, we have decided to use main as our development branch, meaning that it's always on par with the cloud. To protect this branch, all completed feature branches were firstly merged with the testing branch and only after testing merged with the main branch and deployed. To protect the main branch from unnecessary bugs and to have as little conflicts as possible, we made a set of rules. These were not pushing to the main branch unless necessary, creating a new branch for all new issues, aforementioned updating main through testing, and doing as many reviews as possible for merging.
In our project, we have designed a CI/CD workflow that ensures the seamless integration, testing, and deployment of our software, and we're going to walk through the key steps. Firstly, whenever a developer pushes their code changes to a repository, our CI/CD pipeline automatically triggers a series of actions. First, it initiates a clean build of the application using Maven. This ensures that all dependencies are resolved and the application is compiled successfully. Next, we have incorporated automated testing into our CI/CD pipeline using the Maven test command. This step runs our unit tests and tests all of the REST controllers. By automating these tests, we can quickly identify any regressions or issues in the codebase and prevent buggy or dangerous versions from being deployed. Once the code has passed the testing phase, we use Docker to package our application into a container. Docker provides a lightweight and consistent environment, ensuring that our application runs consistently across different platforms. We utilize Google Cloud's container registry to store and manage our Docker images. This centralized registry acts as a secure repository, allowing us to version and distribute our containers effectively. Finally, we leverage Google Cloud Build, a fully managed CI/CD platform, to orchestrate our deployment process. Cloud Build fetches our Docker image from the container registry, applies any necessary configurations, and deploys the application to App Engine. App Engine is a Google Cloud platform that provides a serverless environment for hosting and scaling applications. We have chosen App Engine as our deployment target due to its ease of use, scalability, and managed infrastructure. By deploying our application to App Engine, we can focus on our code without worrying about infrastructure management. To automate the deployment process, we have set up deployment triggers within Cloud Build. Whenever new code is merged into the main branch, Cloud Build automatically triggers a deployment pipeline, pulling the latest Docker image and deploying it to App Engine. This ensures that our application is continuously updated with the latest features and bug fixes. Hello, we are now going to take a look at the cloud part of the of our project. Here we can see the latest version running on Google Cloud SEP engine. We can see it's serving all of the traffic, and it currently has one instance running. If you try to access it, we get unauthorized error, but if we log in and retrieve the JWT token, we can access all of the readings and manage the terrarium. Moving on, we're going to be taking a look at the actual messages being sent from the IoT device to our system. Here we have a message that was just sent with the readings in this payload to port 2. Here we can see the same message with the same data, and we can see that it is stored in our database with the ID 49. If we try to access it, we can do it through localhost using the authorization token we just generated. Here we can find that reading. We can also try to access it using our deployed application, and yeah, here is the same reading. We can additionally configure the temperature limits in our terrarium. Here we have an example of doing that. It's returning OK. And here we have a new downlink with the information that is being sent to the IoT device.
We will now be showcasing the implementation of the IoT device. So without further ado, let's start. I'll start by running the device. So currently it's writing all the code on the board itself. Yeah, we would start now the device. The H term should now start to show us some tasks that are running. Ports are set correctly. Yeah, the board is set correctly. We get a joint network accepted, which means we were accepted by the LoRaWAN network server. And we should see in a short time, yep. We see some data here, some information. We can see that the sensor handler task has been successfully started. The sensor task is responsible for handling all the sensors, which include now the CO2 sensor, the humidity and temperature sensor. We can see that the temperature and humidity task was successfully started, as well as the CO2 task, and we have some values here. We can see the last recorded CO2 value, as well as the temperature, humidity, and with time, the average temperature read would change, giving us an average based on the latest 10 values that we get from the temperature sensor. I would use the messaging utility in order to send a payload. I have one that's being in quit. I'm going to send another one, and hopefully in 5 minutes we can get some more data to work with. Meanwhile, I will speed up the process so you don't have to wait 5 minutes to see basically same data being recorded. So now after we receive some data, we have some working data. We can see that before our default limits were 23 degrees and 26 degrees. Thus, temperature before that was 27.6. That's why the server has turned on. After that, we can see that we have received a downlink payload. This can be seen by going here and seeing that the payload was successfully sent to the device at 8:07, and the uplink, we can see this one, that it also was sent successfully. Now, we have received a downlink with a payload containing the minimum temperature and the maximum temperature allowed for our limit. In this case, it was 24 degrees and 27 degrees. If we scroll down, we can see that the servo has been turned on. We can see that the limits have been updated, now the maximum temperature being 270 degrees. And we can see that the servo has been turned on because the temperature has exceeded the maximum temperature limit.
Let's right now go through the process of setting up and running the test. Currently, I am in project test setup branch, and as we can see, there are two folders, target and test. In target, we do have a file called platformio.ini, and for that, we need to use platform.io extension. So we pick a folder, and we have to choose target folder. We have to wait a few seconds until Platformio configurations are run. Here the new two folders PO and VS Code are added. So we can go back to root folder. We just need to wait a couple seconds until all of the configurations are properly set up. Project is configured, so right now we can click this play button. That will run our tests. As we can see, we have 39 tests. All of the tests are green, which means all of the test passes. We also do have GitHub workflows for both regression testing and coverage testing. It is set up for project test setup. So right now, if I will change something, let's say add a comment into one of the tests, and I would like to push the changes into project test setup, that would firstly run all of the workflows. As we can see in the actions section, we have two workflows that are currently running, one for regression testing and one for test coverage with coveralls. If we choose, for example, regression testing, we can see that there are a bunch of steps that GitHub has to go through before the push can be successfully added into the branch. As we can see, there is also a step for running the tests, and as we can see, all of the tests are passed. That means that this workflow is marked as successful. That would be all for IoT part.
In conclusion, I can say that our team successfully met all the requirements set by our supervisors and implemented multiple use cases, including environmental monitoring, terrarium management, ventilation control, registration, and authentication. The IoT team deployed their code using Microchip Studio and Arduino Mega board, while the cloud team utilized Google Container Registry and Docker, and the front-end team deployed their application using Netlify. Thank you for watching this video.